I should first apologize for not coming back to visit more often. I think I left 8 years ago now, and I've been back twice, so that's not a very good record. I'll try to do better. Um, but before I start talking about this, that I think hopefully you'll find interesting, I just wanted to thank HAO in general for just being, the solid research institution that you are. And I know funding's tight everywhere, and there's contractions everywhere, and it's kind of, dark times in research funding. But from the outside looking in, there's still great research and really good programs in terms of supporting visitors like me, and still hiring postdocs and mentoring graduate students and all that. So keep up the good work. That's my point. Okay, so I'm going to be talking about north-south asymmetries, the solar dynamo and hemispheric coupling. This came about in kind of a funny way. I'd only written one paper about the hemispheres and the coupling. But then I wrote a grant proposal that got rejected. But whoever must have, recommended the rejection must have thought it was interesting enough to ask me to give a talk somewhere. So I was able to go to one of these ISSI conferences, which are really nice programs as well, and had a chance to talk with Paul Charbonneau, who was there, and we got a Space Science Review paper out of it, which has been accepted and should be out any day now after the proofs are corrected. So what you're seeing here is HMI movie of the continuum intensity, and it's just, randomly selected time period, October to November there, 2013. And as we know, if you've been following the solar cycle, the northern hemisphere has ramped up earlier than the southern, and it seemed like it peaked, and then the southern was catching up. And as you can't help, if you're human and scientists like we are, you can't help but notice really cool things like, these weird spots that appear, on either side of the equator that really should have nothing to do with each other. They're so far apart. So we have one sun, but two hemispheres with an unknown degree of coupling. I'll try to review some of the most basic observations of hemispheric coupling, and I'm going to talk about a simulation that Charbonneau and Passos have done, and then kind of get out there a little bit in terms of what we think the coupling mechanisms are, and even unpublished stuff that probably has no business being in a talk, but is fun. So what do we expect to be different in the hemispheres? As you can see from the butterfly diagram, they look pretty damn well coupled. The hemispheres are obviously understanding something about each other, and depending on whether you think the solar dynamo is operating in an advection-dominated regime, you might think that, nothing should be coupled at all, except for possibly stochastic variations that make them look like they're coupled. Or possibly if you think we're working in a heavily diffusion-dominated regime, maybe you think everything should be coupled with just a little bit of stochastic variation making, some random things uncoupled. How can we observe the asymmetry? Sunspot statistics, the tilts of the active regions, the timing of maxima. We can look at the flows. We have observations of the flows in the interior from helioseismology and the flows on the surface, the meridional flow on the surface. So we can look at those flows and look at what the amplitude is and how asymmetric they are across the equator. Then some of the coupling mechanisms that are often found in literature are magnetic diffusivity, transequatorial flux, so just magnetic flux, anything crossing the equator can couple the hemispheres. So the big questions are, what are the limits of the asymmetry? Are the different ways of measuring the asymmetry painting a consistent picture? And is diffusion enough to keep the hemispheres as synchronized as they appear? And can simulations produce the observed asymmetries? Simulations are a whole nother problem. But to bring you, if you're already bored with the talk, I put something in here to keep you awake. I put in the passport photos of myself and my husband. To just remind you that there's, symmetries everywhere, and of course the sun has a mirror symmetry across the equator, but we have a bilateral symmetry as a human, and yet we are not symmetric. If you take the two left sides of someone's face and put them together, they don't look like the person does when you look at them face on. So there's plenty of, slight deviations from symmetry out there, and they shouldn't be surprising. So this is all sort of introductory material. You've seen this before because this plot was made by Scott McIntosh and is in a paper from 2013. So just to kind of get into it slowly so I don't lose you in the second or third slide. You can measure the asymmetries by any measured thing. This is actually the sunspot number. The solid black line is the total sunspot number in both hemispheres, and then you have the hemispheres plotted, and if the northern hemisphere is producing an excess number of sunspots, then you have an area shown as red. If the southern hemisphere is producing an excess number of sunspots, you see it as blue. So it's quite easy to look at this by eye and see in here the sunspot cycle. You've got year along the bottom here, and you can see times when the northern hemisphere is dominating in the rising period and the southern hemisphere is dominating in the declining period, and things like that. And there are some nice databases out there. I mentioned which ones they are up here. I don't know if you end up getting a copy of the talk afterwards, but you can see which data sets do separate the indices. And you can also see in here the north hemisphere in cycle 24 began earlier than the south. So if you wanted to measure that, let's say we wanted to find out, a hard and fast number of how coupled are the hemispheres in terms of sunspot production. I did something very simple in this paper with an undergraduate student, actually, Gallagher, in 2010. And I just summed up all the sunspot area in each hemisphere over the course of the cycle. So that's what's plotted there. Cycles 12 through 23, and you can see how different they are. So we're not talking about at any certain point in time, we're just talking over the entire cycle, what did it produce? And so the average difference is 9%. So this is sunspot area in the north minus the south over the total. So they're usually about, I would say, 10% uncoupled. The maximum, you can see some of the maximum ones, 19. Actually, this is 20% as well. It's just a lower total number of sunspots produced, is about 20%. And if you use sunspot numbers instead of sunspot area, you get something that's painting a consistent picture. So then you can look at the phase of the hemispheres. So they could be producing the same amount of sunspots, but if they're 10 years out of phase, you wouldn't call them very well coupled. So this is another plot by McIntosh, where he was cross-correlating the smooth numbers in the south and the north and finding a phase lag between them in months, which is along the y-axis. So you can see the phase hardly gets above, there's one that's here, the highest one is about 17 or something there, 17 months phase lag. So in general, the hemispheres are coupled within 2 years of each other. And I did it slightly differently in the paper with the undergraduate student. I actually isolated the rising phase of the cycle, the maximum phase of the cycle, and the declining phase of the cycle. I wasn't doing a cross-correlation. I was looking at how much, I called it, I looked at the phase lag when in the rising phase, the hemisphere had produced 25% of the maximum sunspot area. So I looked at it like that. And so the blue curve is the rising phase. It's the shortest phase in the cycle, so it's quite noisy. You can see the blue curve is just sort of bouncing around there. And then at cycle max, you get a more consistent phase lag, and the black curve is the declining phase. So in essence, the phase lags also do not exceed 20% of cycle period, so basically 2 years. So the question is, what mechanism is coupling the hemispheres in orders that they produce sunspot areas within 20% of amplitudes of each other and phase lags less than 2 years of each other? So I would call that a fairly strong coupling, 80% coupling. Not only that, but there seems to be this persistent, that makes sense just from the outset. You would think, well, it's just, something's coupling it, but there's a stochastic perturbation, right? So, it's just a little bit off here or there, 20%. But when you look at McIntosh's plot, and even mine shows it in the declining phase, you see that there's this persistence, not necessarily of the exact phase value, but of the hemisphere that's leading. So you see a hemisphere that's leading, a hemisphere that's leading, a hemisphere that's leading, and it's alternating. And you see that this is Zolotova's paper, where they actually recovered. They went back through historical data sets and created a time series. And you can see this persistence occurring, again, not exactly 4 cycles, but roughly, where the north and south are swapping dominance in terms of who's leading in time. So that's it for the sunspot aspect. So now we're going to talk a little bit about the observed flow asymmetries. Meridional flow can be observed. Multiple cells have been detected by Zhao lately. You can believe that or not. Everyone has their favorite meridional cell pattern, but they do show asymmetries in the hemispheres. So here we've got, let's see what these plots are. So this is showing, I don't know, most of you probably know this, but there used to be considered to be one cell per hemisphere that was pretty well mirrored across the equator. And lately, a recent paper has shown that there's perhaps 2 cells. And so it's a poleward flow at the surface, a return flow at mid-depth, and then, again, poleward deep down. Okay, so that's these 2. This is the figure that is showing the 2 cells here. So this is the 2 different lines are 2 latitudes, one in the north and one in the south. The plot on the left is the 10 to 20 degree north latitude in the north and the south, and then the 35 to 45. And then this is depth, and this is the meridional flow speed. So you can see there are some asymmetries here. It's fairly symmetric here, but then it starts to change down here. Whether you want to believe that or not, go for it. But there's definitely asymmetries observed. So this is a different work done by Rudy Kahm from a 2011 paper that's showing the meridional flow at depth so this is all the latitudes on the left-hand side, the years across the bottom, and this depth is actually 10 to 15 megameters. And overlaid on this is the magnetic contours. And this is the range of speeds that you see. And so you can see here that the northern hemisphere is done producing its majority of magnetic field at the surface, and the southern hemisphere is still producing here. And you can see this, you can almost see the phase lag between the meridional flow here. There's also north-south flow asymmetry seen in the torsional oscillations because the torsional oscillations are often thought of as flow patterns caused by enhanced cooling by magnetic fields. If you have if your dynamo is offset and you have a hemisphere that's leading and the other one's following, you wouldn't be surprised to see the the torsional oscillations are also showing that. In this plot you have, I think the more poleward flow is where you're seeing it here and in here. So you're seeing like a 6 meter per second difference in the higher latitudes in the southern hemisphere than in the north here. And the left plot, I think, is MDI, and the right plot is, GONG, and the right plot is HMI there. So that's it for the observations. Do you have any questions at this point about observations? No? Because now we're entering into the simulations, which is not really my realm. So I put a whole bunch of stuff on here so that I could remember it. No questions about observations? No? Yeah. I thought, Phil, I didn't think you were going to let me down there.
Yeah. No, I just had a simple question that cropped up, which I've noticed. If the sunspots are really kind of the tail end of distribution at night. But there are some people who suggest that sunspots are actually a good measure of what the magnetic field of the sun is on reflecting. Maybe there's a lot of flux on the surface. That's stuff.
Well, I'm an observer. I wrote a paper with some people that do simulations. I'll address it a little bit, but if the surface, the question is relatively like, does the surface tell us anything about what the sun is doing in the interior? If it doesn't, we're in trouble. I think.
It's interesting to me. It's sort of an anthropological principle that
right.
Everything we need to know about the sun rather than the surface, because otherwise you sort of give up. But
well, I don't think that's true. I think you need the simulations. one of the outcomes of this simulation is that they do get a lot of the solar, not all the solar characteristics, but they ended the paper with the question, well, let me get to it. Let me just keep going. But yes.
Is there any indication that there's a greater degree of stochasticity around maximum, the 11-year cycle? Is there any evidence that phase lag is bigger or has more variability during the maximum periods?
You can see in terms of the phase difference here, I calculated it for maximum here. And so you can see the difference between rising phase, max phase, and declining phase here. Okay, so my idea is that actually the phase is set during the cycle. I actually think that the hemispheres couple when the bands come together at the very end of the cycle across the equator, and the hemispheres couple then. And so that's what synchronizes the hemispheres in terms of the dynamo. I mean, it could be not synchronized in all kinds of other ways, but in terms of the dynamo. And so then my guess is that some sort of perturbation of the meridional flow occurs, and they get out of phase. And then that phase just gets more stable as the cycle goes on. So Maoshumi has a paper in 2007 that plots exactly what you're asking, and I could show you that plot. I put it in here and then I took it out because I was afraid I didn't have enough. I was afraid I didn't have enough time. Oh, there we go. And this is actually calculated at maximum. Is that correct, Maoshumi? So this is actually the difference in the so this is a good paper. She uses this information to then use it to input for the modeling, but she looked at the north and south asymmetry. And so this is the fractional north-south spot area difference at maximum. And there's some differences in how you smooth the cycles. And that's what the different curves are there. But so even with this, most of the, so I looked at this and thought, is it really saying something different than what I'm thinking all the parameters are saying? There are a few numbers that are larger, 30% here, and this one is slightly above the 20%, but in general, most of them are falling within the 20% of the differences in the hemisphere. So I think it's painting a pretty consistent picture.
Yeah,
Did you want to say something else? Yeah. Mm-hmm. Right. Okay.
Yeah, the reason it caught my attention is because that 2 years is the time scale for these mid-scale quasi-biennial oscillations. Lots of processes all active.
Right.
And so it could be that 11-year cycle is totally coherent. All the stochasticity is from this second solar event. Something.
Yeah, okay. Okay, so thank you for those questions for the observation. So let's talk about the simulations. They used the ULAG MHD simulation. I don't know how many of you know anything about this. It's an implicit large eddy MHD simulation of solar convection. And it started, I think the principal people that were running it were Gizaru and Racine, and originally developed for terrestrial climate application, maybe even here at NCAR. Yeah. And so then it was adapted for solar purposes. You know, I had a large learning curve with this because I don't usually work with simulations, and I didn't run any of these, but we wrote a paper together, so I had to ostensibly understand most of this. So they call it the Millennium Simulation just because Charbonneau's involved and he likes to do fun things like that. But they ran it for 1,600 years in the time scale of the simulations, which included 39 polarity reversals It's low resolution, 128 by 64 by 48 in the longitude, latitude, and R. I got to talk to Matthias. This is one of the great things about being here. You get to chat with people and hear their sort of informal thoughts on things. Matthias and I were talking yesterday, and he was saying that it would be great to have this increased in resolution to see whether it produced the same results as a test of robustness, and I think that's really important. It spans 0.63 to 0.96 R. Mildly superadiabatic above 0.711, so it's weakly convectively unstable, strongly superadiabatic below. Oh, yes, I'm sorry, yes. Then there's a stress-free upper and lower boundaries where the horizontal B fields are forced to vanish. The magnetic and viscous Reynolds numbers have this range, 30 to 60. The magnetic Prandtl numbers, order of unity. There's thermal forcing, and that sustains the supercritical turbulent convection. There's implicit dissipation. So this is sort of the magic of the code and sort of what I didn't understand, and we tried to talk at the meeting about. And I guess this is just an inherent aspect of these types of codes. But the dissipation is implicit rather than explicit, and it just sort of falls out of the, when you let it run. It just sort of, so it operates in this adaptive subgrid model, and the dissipation is turned on when it's necessary to maintain stability, but then it remains minimally dissipative otherwise. So that's the summary of it. Let's see what it does. So the pros of this, and I know there's a lot of other simulations out there, and if we're just talking about the global MHD ones, there's the pencil and the ash codes, and it would take too long to probably talk about all the differences in them and what they do and what they don't do in reproducing the solar cycle. And so I won't do that, but I am aware that they're out there. So the pros of this one is that it produces the most regular cycles. Its polarity reversals are well synchronized across the hemispheres. It produces an internal differential rotation profile. You see torsional oscillations, meridional flows, including a high latitude cell comes out of the simulations. The bad things about it are that the cycle length is 4 times too long. It's a 40-year cycle. The deep-seated magnetic field is found only at mid to high latitudes, at too high, so it doesn't come down to the equator like we think it should, or that we see in the sun. And it lacks a poloidal, so it doesn't really have a surface, it stops at 0.96, so it lacks poloidal field generation from surface decay of the active regions, okay? So they use these simulations, and you have some cutaways here, and they have a sunspot proxy, which is the squared magnetic flux in this little rectangle here. And then you have the polar proxy, which is the flux that's up at the poles. And they plot that to create, what should be a butterfly diagram, but looks instead like a candle flame or something. And so you can see that the magnetic fields aren't making it down. They should be starting about here and then propagating downward if it was the sun. And they're not doing that. But they do have fairly regular cycles, and they thought, what the hell, let's just go ahead and analyze this 40-year cycle as if it was an 11-year cycle, and let's see what kind of asymmetries we're seeing anyway. So this is the toroidal field, this is the sunspot proxy, and this is the poloidal field, and it's the polar field proxy. So the best way I understand why this simulation is failing, and this is actually a snapshot of the meridional circulation and flows in the interior, so let's not talk about it. But the reason I think that it's failing, from my understanding without being too intimate with it, is that the fields are being generated here, the toroidal field, and they have these longitudinally elongated cells, like the banana cell, where these giant cells across the equator. And they're fairly active, and they're rotating, and they basically just eat up the field as it comes down. So it doesn't get any further than right here. That's why it's stopping. But that's how I understand it.
And this is a single main cell as opposed to the more recent view of the 2 cells?
Okay, they let the meridional flow just develop. They do see, so the question you're asking is, does it actually develop a 2-cell? No, I haven't asked that question. It's fairly complicated, isn't it? I'll have to check. I mean, it does produce a high latitude cell. know that, but I don't know at every step what the meridional circulation is looking like.
It's not an obvious layer.
Right.
Structure. Not-
Yeah, they let it just come out of the simulation, but I should find out. Sorry, I don't know. So let's look at what their simulations do show in terms of hemispheric asymmetry. Yes?
You said that it had trouble generating colloidal fields. Then how does the simulation generate colloidal fields? Cycle, right?
It generates colloidal field, but it doesn't have surface decay.
Okay.
And so it's not from, so yeah, the end result of this, let's see, or was it, maybe I had it there, hold on a second. Oh yeah, so the very last line of the entire paper is this. How important is active region decay on the surface to the operation of the global cycle? Because it generates colloidal field, and it maintains a cycle, and it shows a lot of the singular characteristics of a cycle, but it doesn't have the surface decay like in the classic alpha omega type. So yeah, so it was pretty tantalizing way to end the paper right there with that question. Oh, sorry, I should have mentioned that this isn't our paper I'm referencing. There's a Charbonneau and Passos 2014 paper that looks at a lot of the characteristics prior to the hemispheric asymmetry characteristics.
When had it gone, how to get rid of the simulation of this?
No idea.
It's very diffused.
Who said that? Oh. Okay.
It's not a problem if it's very diffused.
Okay. I don't know. Okay, so looking at the amplitude asymmetry in the simulations, this is similar to the plot I showed of Macintosh, where you've seen the red and the blue if the north is producing more toroidal field that is a sunspot proxy. The takeaway message here is that the amplitudes are high, the asymmetry is higher in the simulation than it is seen in the sun. It can reach up to 40%, whereas we see up to 20%. Yeah.
But this is only a fraction of the
Yes.
hemispheres.
Yes.
Are there that kind of clumping of north and south regions?
Yeah, I'll show you that next. Yeah, yeah, yeah. So the cycles, the north and south hemispheric lengths are the averages are almost exact. You know, yes.
Is the proxy simply linearly proportional to the toroidal field strength or to the square?
It's a square. And then below is the colloidal proxies. But again, and what's obvious here is that you don't have the pi over 2 phase difference at the surface like you do for the sun, because you're not generating the toroidal field from the surface decay. So it's actually in phase with the toroidal field.
I'm colorblind. Are there two colors on that?
But there's blue and red here.
I can see that
And
one.
there's orange and green here. And when they sent me this plot, they were like, ha, ha, ha. No. Yes, there are. And it basically follows exactly. The orange is the North Pole, and it's really high, and the green is the South Pole. So you see it follows almost exactly. Although I should point out that the polar field is actually too high, too, in terms of strength. It's too high from what we see compared to the toroidal field. Okay, so this is the phase lag and the whole cycle asymmetry parameter instead of every time step like we just saw in the previous one. The black line is the phase lag in terms of percent of the cycle length. And it is reproducing what the sun is doing in terms of being less than, or roughly the maximum is 20% out of phase. The asymmetry parameter is too high, as I mentioned before. So the north and south hemispheres in the simulation, you see an asymmetry that's stronger than the sun. Now, something else to mention here is that it's not exactly 4 and 4 like we saw in the sun in terms of the north hemisphere dominating, but you do see, it persisting for longer than you might think if it was just a stochastic perturbation of which hemisphere led. Does that clear? So now we're going to talk a little bit about the coupling mechanisms. What could be coupling the sun's hemispheres? So we're moving beyond the simulations or the observations and just kind of chatting. Magnetic, if you read the literature, people say those hemispheres are coupled by magnetic diffusion. End of story, right there. So that's always been relatively interesting to me. We know it's a turbulent diffusion. We know that it's asymmetric in terms of radius and longitude. And from observations, I'm an observer, from observations we see different observed surface diffusion values depending on the size scale that you look at. I've listed them there in terms of the supergranular diffusivity, the regular size scale magnetic elements, the granular flow, and the plage flows. I just picked out, for no good reason other than it happened to be pictures that I had papers on my computer, some different diffusivity profiles. This is from Declining Gilman. I forget which year. I actually just searched for it, but I forget what year it's from. But this is the diffusivity profile as a function of depth in centimeters squared per second. Up there is a different type of simulation that's being run and other diffusivity profiles. And so depending on what diffusivity profile you adopt, if you're not using one of these sort of implicit diffusion models, like the global MHD ones, you get completely different results. So it's hard to know, the shape of the profile to use, the values to use. I just wanted to point that out. And also, in terms of understanding the diffusivity values, that last sentence there, for example, a 2 times 10 to the 11th value means that the magnetic field could diffuse the entire depth of the convection zone in about 50 years. Just to give you a kind of sense of how these diffusion values are working. And 2 times 10 to the 12th would diffuse in about 10 years. So there's magnetic diffusion that's coupling the hemispheres. Another coupling mechanism might be these longitudinally elongated cells, like the banana cells. They definitely cross the equator. And there is some flow that is north and south. They're mainly doing this. They're rotating, so their flow is mainly in this direction, but they do have some flows that go north and south, and they do cross the equator. These are from the ULAG simulation. It's a snapshot for the vorticity here, so they're showing you the cells. And then this is a snapshot in the equatorial plane that is showing you the flows in and out of the plane. And so the flow crossing the equator from these is basically of the magnitude of the roll speed of the cells, 10 meters per second or so. It doesn't result in a net mass exchange, but it can result in a net pointing flux. So there's also meridional flows that cross the equator as well. So
In the model.
in the model.
Oh, you said there are flows across, meridional flows across the equator within the Chauvenet model.
I was saying it observationally as well, but do you not think that's true?
No, I was asking what you were saying.
Yeah, there are flows that cross the equator in the model, and I think there have been ones reported observationally. I know that some people disagree with them due to errors that they think in the B angle of the sun in calculating them. But I think both in observations and in this model and other models, there are meridional flows that cross the equator. So I wanted to point out a crossing the equator event or time period here in the Maunder diagram. So, this topic of the hemispheres is as old as the hills, maybe not that old. But in 1904, in his paper, he wrote, though the diagram clearly shows a single spot zone in either hemisphere, it reveals a startling and unexpected fact, namely that the southern current not only reaches the equator, but crosses it. And so there are times when the dominant hemisphere is pushing across the equator into the other hemispheres. You can see with the sunspots there. And I don't really know whether it is observed that the meridional circulation correlates with this. I've actually had a hard time pinning it down in the literature. I'd love it if you know those papers of the observed meridional circulation. I'd love to hear which ones they are. So this brings up the topic of a magnetic equator versus a geometric equator. So they don't always line up, right? There is a magnetic equator that can be offset. I mean, if you drew a line through this, you would, if you took the average of the latitude of the sunspot, you would have a magnetic equator that is offset 2 degrees from the geometric equator. And so this causes all kinds of issues. Observationally, one of my favorite topics is that the sunspots that are produced here in the historical databases are often assigned tilt angles that are completely wrong for their magnetic polarity because they're being assumed that they're the northern hemisphere polarity when they're actually the south. But that's another topic altogether. So Pulkkinen reported the magnetic equator as being a 1.8 degree amplitude sine curve with a 90-year period, which would correlate very well with the 4 cycles dominating in the north and then the 4 cycles dominating in the south. Does that make sense? So, other flows that cross the equator. I tried to look at 3 years of HMI data to get a sense of how much flux is actually crossing the equator. Because I had done an estimate earlier, and other people have done this too, where you calculate the amount of magnetic flux that you think is crossing the equator by taking a Carrington rotation map and looking at the gradient of the magnetic field with latitude. And then just assuming that the meridional circulation goes to 0 at the equator, and taking a derivative of it and saying, oh, from diffusion, you assume a diffusion value, and you say some of it, crosses over. And I actually think that's a pretty crappy way to do it. And so I thought it would be better to actually look at the data. And so Keiji Hayashi and I did, and it's not finished yet, it's not published, but this is an example. So we took, initially we took like plus or minus 7 degrees around the equator, and then later on we extended it to plus or minus 11 degrees. So this is a little snapshot of the equator, plus or minus north-south 7.68 degrees. This is 4 days of this single pixel column there. So you can just see what's happening. This is a quiet region. Then this is sometimes, sunspots actually appear on the equator. And so this is one such example. And this is this line, over here is this line, 2 pixels wide, plotted over 8 days. And, there's just not a hell of a lot of flux crossing the equator. I mean, it sits there. It seems to know there's an equator. There is some motion, but it wasn't that impressive, put it that way. So if we look at one of the old ways of the total flux crossing the equator, that's this curve. And let's see, who did this? This is Cameron et al. In 2013, and they compared it. The red line is compared with flux transport simulation for flux crossing the equator. And then if you look at what we calculated from the actual observations of flux crossing the equator with HMI, it would fit into this small time period right here. And essentially, it agrees with what's been found, maybe larger due to, we still have some unit problems actually. But what you see is that the flux begins to cross the equator prior to cycle max, and then it peaks during the declining phase. But the time that you would think that it is crossing the most, which is right at the end of the cycle, at minima, you don't see it crossing very much. And that's because the sunspots are avoiding the equator at that time, and I'm about to talk about that in just a second. But if you're taking the Carrington rotation map and looking at the gradient of the magnetic field you know, the sunspots just vanish near the equator. So you're not seeing this magnetic flux diffusion across the equator. And I kind of feel like, maybe I didn't finish that project because I kind of feel like, so what? Let's say we have an exact value of all the flux crossing the equator. Or let's say we actually know exactly what the turbulent diffusion values are in the convection zone. I mean, are we going to be able to say that that's enough to couple the hemispheres? I don't even know what that value should be. You know, it feels like we should know what that value should be and then look for it and see whether we find enough of it or not. And so I was talking with Douglas earlier, and because we don't know how the dynamo operates, we don't know if it's enough to couple the hemispheres. And he was mentioning, you know, perhaps it's a primordial magnetic field in the radiative zone that's still dominating this. Maybe it's a giant dynamo chicken. I just said that to wake you up. It's laying a giant magnetic egg that hatches into the solar cycle every 11 years or something. But I mean, the obvious mechanism from our current cartoon of, you know, what the dynamo is doing would be that these large magnetic bands that are at the base of the convection zone, if you believe that, are migrating equatorward, and at the end of the cycle, they start to reconnect across the equator, and that synchronizes the cycle. So that's what you would think is doing it, right? So let's look. So I was looking for that. But you have this problem in that late in the cycle, there's all these empty spaces. I know there's a pointer somewhere, but I'll use this umbrella from my hotel. You know, you see that the sunspots, I can tell you what this is. This is a plot from Becker in 1955, and it's isocontours of equal spot frequency from the Greenwich data. So you see the sunspots being produced, you see this nice butterfly wing, and then it reaches very near the equator here, and then you get these voids. You get these empty spaces. That's right when we think it should be connecting, right, across the equator. And so when you're taking the surface map and trying to calculate the diffusion, you're getting zero or very small values here when you think it should be the highest. And so this is another plot that I like a little bit better than the Hathaway plot, because Hathaway has, when he's plotting the sunspot areas, he actually has a width for his location that's a couple of degrees, and it kind of just blurs out the butterfly wings from my eye. So this is from Jan Janssen. He has actually a really nice website that has a lot of the most updated solar plots and things. So we know that sunspots avoid the equator. And so I was looking at this and I was saying, you know, there's this obvious hollow, you know, through here in between the cycles. But it looks like there's actually another hollow that's here, as if the butterfly wings are eroding from the equator upward. And I was thinking maybe that is an indication of a connection at depth. So an active, you know, sort of forced diffusion at depth. And it then stops the production of sunspots. So actually you can't see it, but I'm calling it the ghost thorax of the butterfly diagram, just trying to be poetic, like the Millennium Simulation. And looking into it right now to see how well it stands up to the test of statistics. So the absence of sunspots may be a signature of the leading edges of these toroidal bands canceling each other at depth, and as the opposing currents meet. And what would this look like? I don't see it in the simulations when I'm reading the literature. Perhaps it's there, perhaps I'm not looking for the right keywords or something, but I don't think it'd look like ohmic diffusion. It would be too slow. It wouldn't necessarily be X-point reconnection, which might be too fast. But I think it's something worth looking into and running simulations to see, you know, what really is happening. If there are these super equipartition magnetic fields at the base of the convection zone and they really are coming into close contact across the equator, what does that do? And is that what's synchronizing the hemispheres? Another reason that I think, well, something else that just ties into the coherency of this picture, I should say, is that people plot the locations of the sunspots as a function of time. They plot the centroid of the sunspots. And so this is from a Ternullo 2007 paper where he's looking at, he doesn't smooth the hell out of it so you don't see any of the little features in it. So you can see the middle curve is the centroid location of the sunspot. So you can see it's moving equatorward, but there are these bumps, he calls them retrograde motion. And then, oh, lo and behold, when it kind of flattens out here, you get these big things where the centroid position actually jumps quite a bit equatorward. And I'm wondering whether that is actually the erosion of the magnetic field in the interior through an active coupling across the equator. And that's been reported in many other papers other than this one. I just like this picture. So, in conclusions, the north-south amplitudes are within 20% of each other. The phases are 2 years or less. So I would say, based on the observations of the Dynamo, the hemispheric coupling is greater than 80%. The rising phase is slightly noisy, while the maximum declining phases get more clearly out of sync, may indicate that the coupling occurs late in the cycle. The phase has a long-term persistence of these 4 cycles. Have no idea what that may be from, although it does sort of indicate that it's not a stochastic process. The U-lag simulation reproduces the synchronicity and the persistence in phase. It has a stronger asymmetry in amplitude. And there's actually a lot of details in the U-lag simulation, but I didn't want to kill you with information, so I didn't include everything. Obviously, the community needs stronger constraints on diffusivity and magnetic Reynolds number. And, oh, sorry, I didn't finish that sentence. I'm not sure what I was saying there. Oh, something about what I thought the diffusivity should be, the full diffusivity of the convection zone. But we also need careful simulations of what happens when toroidal fields meet late in the cycle. How is that energy dissipated? Where does it go? And could it actually produce the coupling? And that's all. Thank you. Mm-hmm.
Why, when you have the toroidal fields meeting at the equator and wiping each other out, why would that synchronize the cycle starting at latitude? What's the connection back?
I don't know. It's a good question. Because the other ones could already be started up there. I don't know. I'm sure Scott would have an answer for you. But he's not here. Yeah, I hadn't thought about that. I mean, it seems like maybe it just has to cancel all the flux before the next... I guess it doesn't have to cancel the flux before the next one starts. Yeah, I don't know how it would be communicating with what's at higher latitudes. Maybe not at all.
Well, the Charbonneau simulations are lovely. And Millennium is all right. They weren't the first to have a Millennium simulation.
Okay.
It was in cosmology.
Right.
So, continuing the tradition.
Okay.
But all simulations don't have toroidal field connecting at the equator because his propagation is poleward.
Yes, absolutely.
There's one that Kyle Overson has been running,
Yeah.
which has poleward and propagation of
Equatorward, yeah.
equatorward, plus things. So I think much of the reversal in poles models occurs with what you do close to the poles.
Mm-hmm.
What you do with colloidal field reversal there.
Yeah,
It's fascinating. I mean, these machines are running.
I know. Yeah.
But trying to synchronize an equator across the equator probably is not the case with the Orlando simulation right now.
Oh, absolutely. Yeah, I agree. So you think what's that model called? August one? Is that who is the...
Kyle Alderson, he's a postdoc here at HAM.
Oh, I should meet him. Is he here? No. What's the model called?
Well, it uses the ASH code.
Oh, it's Ash. Okay, that's right. Okay. Okay. I was meant to do this during the questions. I actually work for HMI, even though that didn't have any HMI stuff in it. And so, ask another question. I just wanted to show these are the sharp, what we call the HMI active region patches that are detected automatically and then tracked across the disk. And then for each one of these, it's limb to limb data for this in these beautiful cubes that you can get that I'll show you right now. Ooh, and did you know there was just an X-class flare? I'm sure you know, yeah. So, it's quite easy to these. So we have, for every active region, we have this this is just the continuum intensity, but we have radial field, we have the vector parameters, and it's called the space weather hearts. So anyway, you can access these if you want, if you need more information as to how to get them. But I didn't mean to stop you from asking questions about the hemisphere, but I did want to point out HMI. Yeah.
I was wondering if you could use the coronal morphology images over the last, goes back to 1859, the photographic record for that was scheduled. Those are really nice because, one eclipse a year will give you a nice large-scale magnetic field on the sun. Yeah. May actually address that out of Banner condition if you exist codes.
Horizontal field goes to zero.
Yeah, it seems to me as if, Joan is very aware of the nature of the chrono against the cycles that they themselves. I would think, for instance, you get some minima show the current sheet and a nice symmetric dipolar structure. Other ones show a quadrupolar structure and stuff like this. So it would be kind of interesting to look at. We do have a database at Equator now.
86 is very small, very small. And we were talking years ago about looking at the solar wind data, because you would see for solar wind, one polarity for almost 6 months. And you asked me this years ago.
I actually published a paper that has 0 citations on that.
And what you were saying is that within the being, we couldn't see what the difference was between the magnetic equator and the nuclear. But that's why I could see. It wasn't until it tilted you would actually see the other polarity. So in 86, incredibly, the magnetic equator is incredibly wide.
I did that, or
Not so much less.
Douglas, the paper I'm referring to did look at the structure near the equator at minimum to see how inclined it looked like the colloidal field was, and it was always inclined. It wasn't aligned with the rotational axis.
In 86.
I don't know. I can't remember 86, but it looked like it seemed like there was a preference to be inclined, even at minimum. But you could do that and look at for the quadrupolar as well and see, right? Okay. Yeah. Okay. Yeah.
And I'm not sure if you have mentioned something else. But there's work by Kamodi Mersilov on the Hemisphere current sheet, north-south asymmetry over multiple solar cycles.
Yeah.
Because he refers to the ballerina skirts, the Parker spiral, and he refers to the bashful ballerina for the last few cycles, where the ballerina skirt is very far down.
And you object to Millennium?
Yeah, and that's the northern hemisphere dominating. Yeah, and the magnetic equator being offset from the geometric equator. Yeah, I've seen that. That's good. Okay. Oh, yes.
Since you have these magnificent views, are some of the measures that you ascribe to sunspot area a little bit dubious? What is counted?
Oh, absolutely. I'm using historical databases, so if yeah.
Yeah, but if you were to reinterpret some of your modern exposures for certain things where you have detail, what is being sampled implicitly by historical databases?
Right.
In terms of asymmetry measures and so on, because the systems themselves are very complex.
I understand. Yeah, it's always sort of a luxury to just assume that the data is right and to sort of make conclusions based on that. And I know that's not true. We do have Life Salzard in our group, for example. So he hounds us all the time about the historical databases and the need to carefully make sure they're calibrated against each other and meaningful. And I would really love to have an HMI and MDI database that would be the equivalent. And Fraser Watson has started one in terms of counting sunspots and latitude and longitude and area, but I don't know how consistent it is, and it certainly doesn't have tilts. But it would be nice. It would even be better to be funded for something like that, which is near impossible. But I agree. So you're sort of suggesting either look into the error bars for the old one, or create a modern one.
Well, you have the modern images, at least, you know,
Yeah.
starting with Soho, in terms of high quality imaging, and it would be interesting to ask, 20% isn't that big an asymmetry? Is it that there's diffuse flux around? Much of the field is in big complexes, and how is one also measuring these complexes?
Oh yeah, these were definitely sunspot areas.
Yeah,
There was
exactly.
no field. Yeah, it would be nice to have
But
actual
field
field.
is also next door.
It's true.
I mean, maybe just to follow up, right, if you just plotted the distribution function of magnetic sizes in the hemispheres, do you see the same distribution function with different amplitudes, or do you see a different distribution using HMI and MDI data?
When you say distribution function, do you mean the number with area?
Number in particular area, for example, plus field strength, no flux.
I think Juliana's going to show you that on Friday. She
She
showed. She showed it to me yesterday. You do see some slight differences.
No, the data distribution for that.
I mean, the hemispheres are the same shape, and one is just lower amplitude.
Oh.
Or the hemispheres that are like different shapes, but like the one that has more sunspots is kind of all peaked up at the strong stuff, and the one that has fewer sunspots has the same flux.
Yeah, she didn't look at the different hemispheres, but okay. Thank you.
Give us a reference for your active region pixel for movies.
Oh, it's a little bit complicated. Okay, let me just, you can see the sharp movies on the, yeah, okay, we've got 2 minutes. I can do this. Let me see. So you go to HMI home. You know, this is pretty simple. You can look at the latest images. This is the sharp active region. Well, this is the HARP, the HMI active region patches. You can look at this. And there's monthly. The way I do it actually is there's a website that has all the monthly movies. And I go in and watch the movie. And so the HARP number is not the NOAA number, which just is difficult. But in the movies that I look for, the NOAA number is listed next to the HARP number. So I find the active region I'm interested in, note the HARP number. You can go to the JSOC website, query it with that HARP number, and all the data comes up for that for the 14 days. You know, it's limb to limb. Even if it's prior to, even if it emerges at discenter, you have the entire maximum area from the east to the west. So you can look at it prior to emergence and stuff. And I can help you a little bit if you want more than that, or you can email me. Okay. Thank you.